Okay. Oh, shoot. No, okay. It's going the right way, it looks like. All right. Let's take a look at number 5 and number 6. Very similar questions. Let's say we have a container hanging from a ceiling and pulled to the side to get it out of the way. The rope holding the package is at a 55-degree angle with respect to the ceiling. Well, that would also be this angle, right? Those are those similar angles. I forget what they're called. The angled rope has a tension of 300 newtons. Draw a force diagram, determine the x and y components of the tension, and then how do the forces balance out? This has us write an equation to show how they balance out. And determine the weight of the hanging box. So the weight and force of gravity, right? How they balance out along the x-axis, determine the tension in this rope. So we're trying to figure out the weight of the box and the tension in this rope. So let's go through this in the way that the question asks. So force diagram is first. Draw a dot to represent the object. All right. We got this force of tension. This Sharpie starting to run out from use. All right, and we have force of gravity going down. Fg, we'll call this one. We'll call this one F1 and F2. They're tension forces, but sometimes it's just easier to call them F1 and F2 rather than adding in an extra letter. Then I'm going to put my axis on my coordinate system. I'm going to use dots to represent the axis. Remember, these are not vectors. This is our coordinate system. This is the positive x direction, positive y direction, negative x direction, negative y direction. And the angle 55 degrees is actually here. All right. So that's part A. Part B, determine the x and y components of the tension. All right. That means this F2, really, the angled force, the x and y components. So make a rectangle out of this if we want, right? Where this side, now I'll use dashes for the component of the vector, try to make it stand out against the axis. So this would be F2x, F2y, right? Those are the x and y components of that force. Now, let's make a triangle out of this over here. All right. We know this side is 300. That's the force of tension, 300 newtons. We know this is 55 degrees. All right, so let's figure out the opposite side and the adjacent side, right? So Fx is the adjacent side, so it's going to be F2x, I should call it. It's going to be 300 newtons times the cos of 55 degrees. So, get my calculator here. The x component is the adjacent side, so it's the hypotenuse times the cos of the angle, ca, adjacent, times cos of 55, gives us 69 newtons. All right. Oops, not 120. What am I talking about? 300 times the cos of 55. I was thinking, wait a minute, that doesn't seem right. 170. I only need 2 sig figs here. So F2's x component is 170 newtons. So this side is 170 newtons. All right, that's the x component of that 300 newton force. The y component, F2y, is the opposite side, so it's going to be 300 times the sine of 55 degrees. This should be pretty big, right? 55 is a pretty steep angle. 300 times the sine 55 gives about 250 to 2 sig figs. So F2y is 250 newtons. All right, so that's part B. Force diagram, break the angled vector into components, and then let's figure out how things balance out. So part C says, what forces are balancing out along the y-axis? Write an equation showing how they balance and determine the weight of the hanging box. All right, so I guess I should label these A, B, part C now. In the y-axis, well, F2y and Fg must be equal in magnitude, right? Or they must cancel out, we would say. They must cancel out. So cancel out means they must add up to 0, right? All right, they must add up to 0. So FG has to be equal and opposite to F2Y, right? So if F2Y is 250, right, if this side is 250 newtons going up, then FG must be negative 250 going down, right? So how do I write an equation showing that? Well, I guess I would say a couple ways to do this. You could think of it as like F2Y plus FG must add up to 0. You could say it that way. Or I guess you could say, you know, F2Y must equal FG, right? But actually, you know, it's up to you to make sure you put the negative sign on here. I don't care which way you write this. If you want to say that, or you could say F2Y has to equal FG. You can say that as well. I mean, technically, you really just got to make sure that, okay, F2Y I said was 250. Technically it's positive, right? So therefore, plus FG must equal 0. FG would have to be equal to negative 250 newtons, right? And again, because it's going down. Now the weight, remember, weight is the absolute value of the force, right? So it would just be 250 newtons, right? So if I said force of gravity, you probably wouldn't put the negative sign. If I just say weight, you could just write 250. And you can just tell, right? You know that this side is 250, right? That's 250, got to be 250 going down. Force, you know, then in the x direction for part D, right? F1 has to be equal to F2x component, right? So, and you got to think of these as magnitudes, right? The magnitude, maybe I should write it like that when I do that. The magnitude of the forces have to be equal to each other. The absolute value of the forces have to be equal to each other. So I know this is 170 newtons, so the magnitude of F1 must be 170 newtons. Technically, F1, the actual force, will be negative 170 newtons. I could also write it as the sum like this. I could say F2x, ooh, that's 2x, not tx. F2x plus F1 must be 0. So if this is 170 newtons plus F1 equals 0, therefore F1 would have to equal negative 170. You could also say it like that. Ultimately, the angled force, you know that the adjacent side has to be equal to the force pulling to the left. You know that the opposite side, that y component, must be equal to the force pulling down. All right, so the weight is 250. The tension in this rope here is 170. All right, pretty straightforward. Now, one like number 6, it's a little bit different, given the same setup as problem 5, but with different angles, different quantities, solve it. Okay, so its mass now is 25. All right, and the rope on the left has a tension of 120. Determine the force of tension in the angled rope and the angle it makes with the ceiling. This is one where, you know, we will be able to find out the x and y components of the angled force. Then we use the triangle to figure out what's going on. All right, so okay, I'll call this again F1, F2, and FG. All right, FG is mg. FG is going to be negative 250. That you should be doing quickly at this point, right? You know the mass is, you know, again, it's mg. It's 25 kilograms times about 10 newtons per kilogram. The negative sign comes from, you know, this is mg. The negative sign comes from the direction, all right? The rope on the right has a tension of 120 newtons, so we'll put negative 120 newtons there. All right, so F2 now, all right, x and y, f2x, f2y, right? So I know automatically that this has to be 250, this has to be 120. So it's a little different than the last problem here. So this is, so let's make a triangle out of this, right? Make the rectangle. Maybe I don't put the axes on this diagram just to make it a little bit easier to see what's going on, right? So, things you want to declare, okay? I probably want to make sure I say the magnitude f2x is equal to the magnitude of f1, right? That's the x direction. In the y direction, what's happening? All right? So now I don't have the framework here that I had in problem 5. I draw the force diagram, right? This is our angle theta. I can break this up into x and y components. I kind of did that already, break into x and y components. That's kind of step 2. So force diagram, x and y components, and then see how the forces balance. All right, in the y direction, f2y, the magnitude of that must equal fg, right? So really easy. I can look at the trig now. Draw the trig down here. This is theta. Okay, if this is true, then F2x has to equal 120 newtons, and F2y must equal 250 newtons, right? So 250, 120. Now, to get the magnitude, get this, you can do a couple things here, right? I can do Pythagorean's theorem to get F2. This is F2, right? So I could say F2 squared equals 250 squared plus 120 squared. So F2 is the square root of, let's go ahead and, of 250 squared plus 120 squared. So second square root, make sure there's parentheses in there. I think this calculator automatically would have done it right, but hey, better safe than sorry. 280. So F2 has to be 280 newtons. All right, so that's the magnitude of the angled force. Now I need theta. Well, now we could do anything. We could do sine, cosine. I like to use tangent myself. I like to use tangent because these numbers are the known ones that we use. So I'm going to say tan theta equals opposite over adjacent. I'm going to leave a little space here because I know what's going to happen next here. So tan theta equals opposite over adjacent, TOA. Tan theta equals opposite over adjacent. Now, how do we solve for theta? We take the tan inverse of both sides. Hopefully you remember that. And tan inverse of tan gives us theta. Sometimes people call it the tanverse. The tanverse of 250 over 120. That's kind of a joke, inside jokes. I think somebody in class once said it that way, and it was kind of funny, and we've stuck with it. 64 degrees. So that makes sense. 64 degrees. 64 degrees. All right, that makes sense because if we look back to the last one, right, it was 55 degrees, but our x component was bigger. It was 170, not 120. So there's that one. Number 7 is actually, while we're at it here, this video's not too long. Number 7 is pretty much the same. Just again, it's kind of going we're going to know a little bit more here. So it's a tram, weight of the tram. All right, let's draw the force diagram. Holy cow, this is a really steep angle now, right? F1, F2. This is 75 degrees with the vertical. Now, I think what most of you are going to want to do with this, and FG, right? If this is 75 degrees, this must be 15 degrees, right? We usually like to have that angle relative to the x-axis. It says determine the weight. It says the left cable is 30,000 newtons. So we got a big number here. 30,000 newtons, and let's see. determine the weight of the tram. So we're trying to find FG. All right. So what do we have here? Well, let's look at the X and Y components. So we drew the force diagram. Now we're going to examine the X and Y components of the angled forces. F2X, F2Y. Okay, cool. So in the X direction, now I know that F2X has to equal 30,000 newtons. So I can just jump right to that, F2X, right? I basically am saying, you know, I could do this. The magnitude of F1 has to equal the magnitude of F2X. That's going to be 30,000 newtons. So this has got to be 30,000 newtons on this side. It's positive. This one technically is negative, but it's okay. All right. So let's draw a triangle here and get going. So I know this is 15 degrees. I know the X component has got to be 30,000. I need the weight. Well, where's the weight? Well, I kind of didn't do a good job drawing this to scale, right? This FG vector probably should have been quite a bit shorter because we know in the Y direction that the magnitude of F2Y has to be equal to the magnitude of gravity. All right? So if I can figure out F2Y, I know what the weight is. Magnitude of gravity is weight. All right? Cool. So the weight, magnitude of gravity, it's this side of the triangle, the hypotenuse, or the opposite side of the triangle. This is going to essentially be the weight. So we do so. All right? So katoa. Or no, sorry, tangent. Tan of 15. Look at the trig here. Tan of 15 degrees equals opposite F2Y over adjacent 30,000. All right, multiply both sides by 30,000. Boom. We get F2Y equals 30,000 times the tan of 15 degrees. Sweet. 30,000 times the tan of 15. That's going to be 8,000. 8,000 newtons is the Y component, therefore the weight is positive or negative 8,000, or you know, the magnitude of the force of gravity is the weight. It's 8,000 newtons. Well, that's a fun one, right? So it becomes repetitive, right? You draw the force diagram, step one. So just to kind of recap, step one, right? Force diagram. Step two, look at X and Y components. Sometimes, like in number 5, for instance, you're going to figure those out. You're going to calculate them right away. If you know the value of the angle vector and vector, you calculate them right away, the X and Y components. If you don't know them, then you just kind of draw them and start thinking about them, right? Step 3, see how the forces balance. All right, see how the forces balance. All right, and then step 4, you know, it's basically figure out the answer. Figure out the answer. I don't know how to say it other than that. Do the algebra. Do the math. All right, so pretty basic procedure there. That applies to all force problems at the end of the day. Force diagram, look at the trig, the geometry, figure out how the forces balance and add up, and then finally do the math. All right, have a good one.